Okay, everybody, I'm going to go through this pretty quickly because I have a very limited amount of time. So I might even just do half of this probably and then the other half later. All right, we're going to go ahead and start with this first problem. We're going to change this to 0.158 liters, and anytime we have a liters of a mole per liter solution, 1.4 mole per liter, we multiply them together. So we're just going to multiply them together. So we have 0.158 times 1.4, and that gives us 0.2212 mole of sodium phosphate. Now we can read the rest of the question. Sodium phosphate reacts completely with strontium sulfide. Phosphate and sulfide are going to switch in this double displacement reaction, and we'll get Na3PO4. So in other words, sodium phosphate plus strontium sulfide will form sodium sulfide and strontium phosphate. Okay, so this is the reaction we have right now. It's not balanced. We probably ought to balance it, so let's go ahead and do that. I got 3 sodiums and 2 sodiums here, so I need a 2 there and a 3 there. Now I've messed with the sulfur, so I have 3 sulfurs, and now I need 3 there, and that works out really well, so now the problem is balanced. All right, again, we have 0.2212 mole of this Na3PO4. We want to know how many total ions are in solution. The solubility of strontium phosphate is insoluble. It's a solid. However, the sodium sulfide is actually going to be aqueous, meaning it's dissolved in solution. So in solution, it actually breaks down into 2 Na plus and 1 S2 minus. So it would have 3 ions, 1, 2 from the sodiums and 1 from the sulfur. So let's go ahead and figure out how many moles of this we'd have. If we can figure out how many moles of this we have, we can figure out molecules, we can figure out ions. So we have 0.2212 mole of the sodium phosphate. We know for every 2 mole of sodium phosphate, we get 3 mole of the sodium sulfide. Now we're in sodium sulfide town, but we need to go from mole to formula unit town. We know a mole of anything is 6.022 times 10 to the 23rd of those things, but what we're talking about here is sodium sulfide. So we're talking about formula units of sodium sulfide. We know 1 formula unit of sodium sulfide has 3 ions. And if you calculate all this out, this times that, times that, times that, divided by 2, you get an answer of 6.0 E23 ions. Moving on to the next one, zinc sulfate reacts with strontium nitrate. So this is aqueous, is going to react with strontium nitrate, and it's going to form zinc nitrate and strontium sulfate. If you looked at each of these things, I wrote aqueous automatically here because it's aqueous. Anything with nitrate is aqueous. The only thing that's solid is this guy. So when it's asking for the net ionic equation, it's saying what things did not break apart or what was actually formed. So if you look at zinc, for example, in the solution, over here it's aqueous, meaning it's broken apart. And on the product side, it's also still aqueous, it's still broken apart. So anytime something's aqueous, it remains broken apart in solution. Here, it's put together. That's why this is what we're interested in. Our total, or our net ionic equation is SrSO4 solid, and all we have to do is say, okay, how did we form this? We formed it with a strontium 2 plus and a sulfate. This is our net ionic equation. You just look for the solid thing, aqueous, 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 solid. You underline the solid and ask how you made it. There will be cases where everything's aqueous, in which case there was no reaction which took place. There will be cases where both things are solid, in which case the net ionic equation must include all things. Those are just potential examples. All right, density of 1.2 mole of helium gas at STP. Okay, this is actually kind of a trick. It's not necessarily a trick, it's to test to see if you really understand, because if we have 10 grams of water, or 10 million grams of water, it all has the same density of 1.00 grams per mole. So it doesn't matter how much we have of something, at a certain temperature and a certain pressure, the density is going to be the same no matter how much we have. In fact, you'll see this if you have the equation for density memorized for a gas, which is density equals pressure times molar mass over R times T. In this case, our pressure is 1.00 atm because we're talking about standard temperature and pressure. That's 1 atm for the pressure, and the temperature is 273.15 Kelvin. That's what STP tells us. So here we have pressure times the molar mass of helium, which is 4.002 grams per mole, all divided by the gas constant, R, 0.0821 liters atm over mole Kelvin, times the temperature, which again is 273.15 Kelvin. If you calculate this out, you'll find out the density of helium, no matter how much you have, the density of helium at STP is 0.178 grams per liter. Moving on to the next problem. This is pretty straightforward, PV equals nRT. It says assume the gas acts ideally. If it doesn't act ideally, then you pretty much don't know what to do at this current point in time, and that's okay. That won't be on the exam. We're going to turn 108 grams into 2.54 mole. Anytime we got mole, we got volume, we got temperature, it's looking for pressure, we ought to automatically think PV equals nRT. In this case, we're looking for pressure. So pressure equals nRT over V. All we do is plug and chug. This is 2.54 mole. So gas constant 0.0281. I'm going to leave the units out just in an effort to save time. Our temperature is 293.15 Kelvin. And we're going to put that all over 2.0 liters. It gives an insane pressure of 48 atm. On to the next one. Woo, one of my faves. This one's so fun, you guys. Okay, first thing you should notice, it gives us liters, atm, some other information. We ought to be automatically thinking PV equals nRT. Anytime you're given a volume, a pressure, and a temperature, you can solve for moles. So in this case, we have a volume, pressure, and temperature. We can solve for moles. We can solve for moles because N equals RT, or excuse me, equals PV over RT. I can do it. And in this case, our pressure is given to us as 1.2 atm. Our volume is 1.5 liters. R is 0.0821 liters atm per mole K. And our temperature is 293.15 Kelvin. I just realized I messed up here. I used the wrong pressure. Or excuse me, wrong temperature. This should be 473.15. But you'll get this answer. That answer is correct. Okay, on to this one. So once you calculate this out, you find out that the number of moles of this is 0.07479. Moles of what? Mole of some kind of gas. It could be a mixture of gas. We don't know. We have to look and see what happens. So we know that we have this many mole of gas just given this information. The other thing we see is grams. We always put grams into moles. Grams of sodium metal tells us we're talking about a metal. Is a metal a gas? Hopefully not. And this is going to give us a number of moles, which is 0.16964 mole. Essentially, we took 3.9 and divided by the molar mass of sodium. Okay, so now we're sitting over here. We have 2 sodiums plus 1 chlorine gas going to 2 sodium chloride. Sodium chloride is a solid. We should recognize it as table salt. So therefore, when we talk about moles here, this must be Cl2. So over here, we're talking about 0.07479 mole of CO2. And again, the sodium we have is 0.16964. So we have moles of sodium, moles of chlorine. We're trying to figure out this and then put it into grams. No big deal, total normal stoichiometry, we're used to it. We gotta find the limiting reactant, divide that by 2, divide that by 1, ask what's smaller. You will see that the limiting reactant is chlorine. So that's why we're gonna start with chlorine, 0.07479 mole of chlorine. I know for every 1 mole of Cl2, I get 2 mole of sodium chloride. I know a mole of sodium chloride has a mass of 58.44 grams. And if you calculate this out, you'll find out that 8.7 grams is how much you can make. All right, so important things to note in this, always turn grams into moles, turn PV and T into moles as well. All right, we're moving right along. So on to number 6, maybe we can finish this all. Maybe. All right, on to number 6. It says calculate the standard enthalpy for the following reaction. We have enthalpy of formation, kilojoules per mole. What that tells you is how much energy it took to form 1 mole of this stuff. So for O2, it took 0 enthalpy, change in enthalpy to form the oxygen. For NO2, it took 33.18 to form 1 mole, but we don't have 1 mole, we have 2 moles. And then same with over here, the NO, we had 2 moles, so we gotta calculate that in. So what we're gonna do is we're gonna take 2 for the NO2 times 33.18 kilojoules per mole. And this is mole we're talking about here. So 2 mole times this, the moles will cancel and we're left with kilojoules. This gives us 66.36 kilojoules. And we move over here to this one. Here we have 2 mole of NO times 90.25 kilojoules per mole. And then oxygen is 0, so we're essentially taking 1 times 0. If we calculate this, this is 180.50. If oxygen had been something, we would add that to this as well. So essentially we're drawing a line right here. And we're saying calculate everything on the reactants, on the reactant side, and everything on the product side. We're gonna take products minus reactants to give us the total enthalpy of the reaction. Delta H of our reaction is going to be everything on the product side, 66.36 kilojoules, minus everything on the reactant side, 180.50 kilojoules. And if you calculate this out, you get negative 114.14 kilojoules. In other words, in order for 2 moles of NO to react with 1 mole of O2 and form 2 moles of NO2, it will release 114.14 kilojoules. Number 7, in a car, expanding gases push on the piston and do work. The expanding gases do work, meaning the work is negative. Then it says, meanwhile the car gets hot and releases. Q must also be negative because it's released. There's this equation that is delta E equals Q plus W. We know our Q was the heat. It's negative 224 joules. We know our W is the work. It's negative 842 joules. The total change in energy of the system is negative 1066 joules.